It's quite a difficult one, but not as long as the last one. It's important. This algebra workout is all about something called modular arithmetic. So we're going to be doing arithmetic with integers, but we're going to be doing it in a slightly different way, and we're going to be very concerned about the remainders when you divide numbers by other numbers.
Well, here are the problems we're being asked to do. The first problem is to find the remainder when 2 to the power 100 is divided by 7. Now, you might be tempted to use your calculator, but that will only give an approximation for 2 to the power 100. But you'll see that this is in fact a very straightforward problem. The second problem is to calculate the answers to these. 7 plus 19. Well, that's very straightforward. But notice this 30. That means add 7 to 19 modulo 30, and we'll explain what that means later. The next part of this problem is to multiply 7 by 19 modulo 30 again. And the third problem is to solve this equation, where 7 is multiplied by x modulo 30, and the result is 1. So we've got to find x. And one more final problem will involve you in solving a message that's been enciphered, and I'll explain more about that when we get to it. So what mathematics do we need to solve problems like these?
Well, in order to solve that first problem about the remainders, Sarah's going to have to use an idea called congruence. So let me explain that first. Here's a congruence. A is congruent to B mod n. And what that means is the following. If you divide A by n, and then if you divide B by n, the remainder in each case will be the same. Alternatively, if you take A and B and work out the difference between them, A minus B, then that difference will be divisible by n. And either of these definitions do to show that A is congruent to B mod n. Let's try an example. Let's take the congruence. 25 is congruent to 3 mod 11. How do we check that? Well, first of all, divide 25 by 11. And 25 divided by 11 is 2 remainder 3. And it's the remainder 3 that's important. Because if we then divide this 3 by 11, that's 3 divided by 11, then we get 0, remainder 3. The remainders are the same in each case, so that 25 is congruent to 3 mod 11. Now let's try another example. Let's try an example where we have a negative number on the left-hand side. And in this case, we'll have negative 26 is congruent to 7 mod 11. And we want to check that. Now, it's quite difficult to actually divide negative 26 by 11 and find a remainder. So let's use the alternative approach. Let's find the difference between negative 26 and 7 and see if it's divisible by 11. Well, of course, negative 26 minus 7 is negative 33, and that is indeed divisible by 11. So this statement is indeed true. Negative 26 is congruent to 7 mod 11. OK, let's go on then and look at some of the properties of congruences. Let me take two congruences, A congruent to B mod n and C congruent to D mod n. The modulus the same in both cases. Now you can actually add congruences. So if these two statements are correct, we can say that A plus C is congruent to B plus D mod n. But not only can you add congruences, you can also multiply them. A times C would be congruent to B times D mod n. Let's just for a second look at the second statement and imagine that if A was equal to B, what would happen here? Well, if A and B were the same, we could rewrite this as AC is congruent to AD mod n. And this gives a very important general property that for any integer k, kc is congruent to kd mod n. Well, the first of Sarah's problems was to work out 2 to the power 100, and Sarah has to work out the remainder of that when she divides by 7. And that's just like saying, what is 2 to the power 100 congruent to? Mod 7. Well, because of that property about multiplying congruences, it suggests that what we should do is work out the successive powers. And that's exactly what Sarah will do. she'll work out 2 to the power 1, and that's easy. 2 to the power 2, and that's nearly as easy. 2 to the power 3, and so on. And each time she'll work out the remainder, modulo 7, and see if there's a pattern.
Right, so I'm going to work out the successive powers to see if there's a pattern. And I've done the first couple. 2 to the power 1, well, that's just 2. If I divide that by 7, I get a remainder of 2. So 2 to the power 1 is congruent to 2 modulo 7. 2 squared, well, that's 4. Divide that by 7, I get a remainder of 4. So 2 squared is congruent to 4 modulo 7. What about 2 cubed? Well, 2 cubed equals 8. And 8 divided by 7, well, that's 1 with a remainder of 1. And it's the remainders we're interested in. So 2 cubed is congruent to 1 modulo 7. What about 2 to the power 4? Well, I could do that one of two ways. I could either say 2 to the power 4, well, that's 16. Divide 16 by 7, I get 2, remainder 2, so my answer would be 2. But there's another way I can do it, using the multiplication rule for congruences. If I take both sides, 2 cubed, multiply that by 2, my answer will be 1 multiplied by 2. So I'm multiplying both sides by 2. So 2 to the power 4, which is 2 cubed multiplied by 2, that's congruent to 1 multiplied by 2. So that's 2. So the answer is 2 modulo 7. And I'm going to use that same method to work out 2 to the power 5. So 2 times 2, well, that's 4. So 2 to the power 5 is congruent to 4 modulo 7. And I'll use the same method for 2 to the power 6. But 4 multiplied by 2, well, that's 8. We saw earlier that 8 divided by 7 gives me a remainder of 1. So 2 to the power 6 is congruent to 1 modulo 7. Now I can begin to see a pattern forming. So my numbers are going 2, 4, 1, and that's repeating 2, 4, and 1. Now, when is it 1? Well, every time I've got a power that's a multiple of 3, so here 2 cubed, that's congruent to 1 modulo 7, and 2 to the power 6, that's congruent to 1 modulo 7. So from this, I could work out, for example, 2 to the power 9, that's going to be congruent to 1 modulo 7, because 9 is a multiple of 3. So in general, I could write that down as 2 to the k is congruent to 1 modulo 7, where k is a multiple of 3. Well, let's remind ourselves of what I wanted to work out in the first place. I wanted to work out the remainder of 2 to the power 100. Well, 100 isn't a multiple of 3, but it is one more than that. It's 2 to the power 99 times 2 to the power 1, and I think that's going to help me. So 2 to the power 99, well, 99, that's a multiple of 3, and I know, therefore, that it's going to be congruent to 1 modulo 7. And then I can use that multiplication rule. So 2 to the power 100, that's multiplying 2 to the 99 by 2. That's going to be congruent to 1 multiplied by 2, so that's 2 modulo 7. So that tells me that the remainder, if I divide 2 to the power 100 by 7, is 2.
When Sarah was working out that sequence of congruences, remember what she was doing was multiplying both sides of the congruence by k. And in her case, k was equal to 2.
The second problem involves this funny addition. I've got to work out 7 plus 19 modulo 30. Now, addition modulo 30 is just like ordinary addition, but on a different set of numbers. This is all to do with remainders. In these problems, remainders on division by 30. To see exactly what this means, here's Alan.
Well, let's look at the ideas with a smaller set. For example, the remainders you get when you divide by 7. This set is written z, that's z as in integers, z with a small subscript 7. And it's the set of remainders you get when you divide any integer by 7. So that would be 0, 1, 2, 3, 4, 5, or 6. Now, in general, instead of z7, we could have zn, and zn would be the set of remainders you get when you divide by n. That would be 0, 1, 2, all the way up to n minus 1. Now let's consider what happens when we add within this set. So let's take an a and a b, and let's add them, a plus b modulo n. What does that mean? Well, it means the remainder, when you take a plus b, add it normally, and then divide by n. Similarly, if you wanted to take a and b, and instead of adding them under modulo n, multiply them under modulo n, then again, you would get, in this case, the remainder of a times b when divided by n. Let's do a couple of examples. Let's do 2 plus 6 modulo 7. Now, the modulo 7 tells you that you're working in Z7, the set of remainders when divided by 7, 0 up to 6. Now, 2 plus 6 is not in this set. 8 is not in the set. So we take the remainder of 2 plus 6 when divided by 7. 8 divided by 7 has remainder 1. If we wanted to multiply the 2 and the 6 under mod 7, that would be 2 times 6 modulo 7. Then 2 6s are 12, not in the set. So we take the remainder of 2 times 6 when dividing by 7. In that case, 5. So 2 times 6 mod 7 is equal to 5.
OK, so I'm going to do these sums the way Alan's described. Well, the first one, 7 plus 19 modulo 30. Well, 7 plus 19, that's 26. And I need to divide that by 30. And if I do that, the remainder is 26. So that's 26. And I could have written that down as 7 plus 19 is congruent to 26 modulo 30. Now, what about the multiplication? Well, 7 multiplied by 19, that's 133. Now I need to divide that by 30. Well, 4 30s are 120, so that gives me a remainder of 13. So 7 times 19 modulo 30 is 13. Right, so having done an example like that, I've got a more challenging problem. I've got to solve an equation 7 times x equals 1 mod 30.
So what Sarah wants to do is to find a number x with the property that 7 times x equals 1 using modulo 30. Now, by using modulo 30, we mean we're working in Z30, which is the set of remainders when you divide integers by 30, 0 up to 29. And what we want is 7x to equal 1 plus some multiple of 30. Let's say 1 plus 30k. So, if Sarah can find an x with that property, then she'll have solved the problem. And she's going to do that using an ancient technique, Euclid's algorithm.
Well, Euclid's algorithm is a method that's based on repeated division, so I'm going to have to do some arithmetic here. I'm going to start with the numbers 30 and 7, which is the numbers that I've been given, and I'm going to divide the larger by the smaller. So that's 30 divided by 7. And that gives me 4 with a remainder of 2. Well, now I'm going to do the process again. I've used the 30, so I'm going to now use the 7 and again divide the larger by the smaller. So 7 divided by 2. And that gives me 3 with a remainder of 1. Well, now the process of division has ended because I've only got a remainder of 1 left here. And because I'm going to work with these equations further, I think I'll simplify them a bit. So I'm going to take this equation, I'll multiply both sides by 7, and that gives me 30 equals 4 multiplied by 7, plus the remainder, that's 2. And rearranging this equation, well, I'll multiply both sides by 2, and that gives me 7 equals 3 multiplied by 2, plus the remainder, 1. And then, as Alan found, we take these divisions and rearrange them to obtain an equation of the form 7x equals 1 plus 30k. So I'm trying to find an expression 7x equals 1 plus 30k. And don't worry, it isn't as bad as it sounds. Now, in my target expression, if you like, I've got this 1 here, so I think I'll start by trying to find an expression for just 1, and I can get that by rearranging this second equation here. So solving this for 1 gives me 7 minus 3 multiplied by 2 equals 1. Now, there is another way that I could express this 2 here, for example, by rearranging this equation here. So if I rearrange this to 30 minus 4 multiplied by 7 equals 2, I could substitute this value in here for this 2. So if I write that out, I'll get 7 minus 3 multiplied by, and instead of the 2, I've got 30 minus 4 multiplied by 7, and that all equals 1. Now, because I'm aiming for 7x here on the left-hand side, I think it might be a good idea to gather the 7 terms together. So I'm going to multiply out some of these brackets, but not all of it, because if I did that, I'd just end up with 1 equals 1. So gathering together the 7 terms, well, I've got negative 3 multiplied by negative 4. That gives me plus 12 multiplied by 7. So that's 12 sevens, plus another 7. So that's 7 times 13 minus 3 times 30, and that all equals 1. Well, now, if I take this term here, negative 3 multiplied by 13, put that onto the right-hand side, I get 7 multiplied by 13 equals 1 plus 30 times 3. So 7 times 13 is equal to 1 plus 30 times k, where k is 3. So I've solved the equation. I've found that the equation 7x equals 1 modulo 30 has the solution x equals 13.
Now, whenever you've solved a modular equation like this one, you can always check the answer by multiplying it out. So we could multiply 7 times 13. 7 times 13 is 91, but we're working in modulo 30, so dividing by 30, 91 divided by 30, remainder 1. So indeed, 7 times 13 modulo 30 is 1. If you're worried at any time that you've made a mistake, you can always check.
And finally, we've got to decipher this sequence of numbers. It represents a 6-letter word. Each of the 6 letters was turned into a number in the obvious way. So A is 1, B is 2, C is 3, and so on. Then those numbers were multiplied by 7 modulo 30 to produce these 6 numbers. We've been given these numbers, and what we've got to do is to somehow work out what the original numbers were. Well, Alan's going to explain how we can use our answer to the last problem to do this deciphering.
Yes, indeed. Well, it's helpful to have a diagram here to explain what's going on. So you can see here in this diagram that on the left we have the message text M, and on the right the ciphertext C. This is the text that Sarah actually has. Now, each number in the message text is enciphered by multiplying it by 7, mod 30. And when you multiply the message text numbers by 7, they become the ciphertext. And what we need to do is find some way of getting back from ciphertext to message text. Now, you probably remember an equation we saw just a few moments ago. 7 times 13 mod 30 is 1. This means 7 and 13 are multiplicative inverses under mod 30. And this is a multiplicative cipher. So if we have enciphered using 7, we decipher using the 13. So to decipher, we multiply each element in the ciphertext by 13. Say these were the 6 elements of the ciphertext, C1, C2 up to C6. Then individually, we need to take each of these and multiply them by 13. And if we do that and reduce it by mod 30, we get the message text. In other words, we get M1 from the C1, M2 from the C2, and then M3, 4, 5, and 6. So, if you've enciphered by multiplying by 7, then you decipher by multiplying by the multiplicative inverse of 7, that's 13, where 7 times 13 gives you 1 mod 30.
OK, so what I've got to do then is multiply by 13 and find the remainder modulo 30. Well, the first number I've got is 5, so 5 times 13, well, that's 65. And 65 divided by 30, well, that's 2. Oh, with a remainder of 5, which is my original number. Now, that just happens to be the case. It won't usually be. So, substituting in 5 into my table, well, that gives me my first letter, which is E. Now, my second number, well, that's 27. So, doing the same thing, 27 multiplied by 13. Now, I confess, I've already worked that one out. It's 351. So then I divide 351 by 30. Actually, that's not so hard because 11 times 30 is 330. So that gives me 11 with a remainder of 21. And 21 in my table gives me my second letter, which is U. Right, I'm going to give you the rest of the answers now, but if you want the satisfaction of working them out for yourself, look away now.
Well, in a fairly short time, we've gone from the very basic principles of modular arithmetic to a fairly sophisticated enciphering and deciphering algorithm. And all thanks to Euclid and his remarkable achievements over 2,000 years ago. Well, until next time, that's all from us. Bye for now.
Goodbye.